Hello everyone, we are excited to present our embedded systems project titled Microcontroller Based Washing Machine Simulation using PIC Lab. This project was part of our internship with Emertxe Information Technologies Private Limited, a leading name in embedded systems training. Our team includes Ronak Singh, Gautam Sharma, and Pirisangala Tanmay and myself Prachi Phunde. We've collaborated over the past month to build and simulate this entire system from scratch without using any physical hardware. We'll walk you through our journey, our understanding of embedded systems, and how we applied that to a real world scenario, creating a smart washing machine interface. These are the contents that we'll be presenting, from everything that we learned to implementing all that into this project. This was a 1 month internship with a very practical approach. The goal was not just to learn embedded C programming, but to apply it through a full fledged simulation based project. And the best part was, we were given a real world problem to solve and industry standard tools to work with. Our learning was hands on and structured, including understanding microcontroller architecture, working with simulators, designing logic like timers, interrupts, and input output handling, and finally integrating everything into one application. Another highlight is the fact that this opportunity was completely free of cost for selected students. It was an amazing chance to grow and explore, especially for students like us eager to apply what we have learned in our college. Overall, this internship bridged the gap between academic learning and real world embedded system development. Every phase of the internship was aligned with specific learning goals. Let's see the goals of this online internship. We gained hands on experience in embedded C programming, which is at the heart of all embedded applications, which helped us develop our skills. We worked with the PIC 16F877A microcontroller, exploring how internal registers, input and output ports, timers, and interrupt handling actually function. This helped us understand hardware, and we used MPLabX IDE for code writing and debugging, XC8 compiler for generating hex files from C code, Pixim Lab, a powerful simulation tool where we connected virtual switches, displays, and microcontrollers. End-to-end project lifecycle experience, from understanding requirements, designing state diagrams, writing code, to debugging and simulating output. It was a mini version of a real industry project. These goals helped us become confident not just in coding, but in understanding how a complete embedded product comes to life. Overall, skills development, understanding hardware, mastering toolchain, and project lifecycle experience were the goals of this internship. So, before we explain our washing machine project, let's take a moment to understand what an embedded system really is. An embedded system is a dedicated computer system designed to perform a specific task. Unlike general purpose computers like laptops or phones, a combination of computer hardware and compute and software designed to perform a specific dedicated function. It is often part of a larger system and may not have a traditional user interface like a PC. Some examples you might recognize are microwave ovens, smartwatches, washing machines, medical devices like insulin pumps, etc. These systems typically have limited resources and they must run reliably and consistently for a long time. The main components of an embedded system are microcontroller. Think of it as the CPU of the system, the memory for storing data and instructions, and input output peripherals, which include buttons, displays, sensors, monitors, etc. Our project simulates all of these in software, giving us a clear idea of how these components interact in real life scenarios. Embedded systems can be classified based on how they function and how time sensitive they are. Based on functionality, we have standalone embedded systems and network embedded systems. And based on time criticality, we have hard real time systems and soft real time systems. Let us see embedded systems based on functionality. Standalone embedded systems They work independently without requiring a host system, generally designed for a specific dedicated task. For example, we have washing machine and microwave. Our washing machine is a perfect example. It doesn't need the internet to work. Now let us see networked embedded systems. These are connected to a network to share data or resources with other systems. They can communicate with other devices over protocols. For example, home automation system like smart lighting connected to your phone or Alexa. Now let us see embedded systems based on time criticality. In hard real time, missing a deadline results in complete system failure. Failure to respond on time can lead to system failure or even danger. For example, airbags in a car must deploy at the exact moment. These require strict timing guarantees with minimal jitter. Another example of hard real time embedded system is a pacemaker. Then we have soft real time embedded systems. In this, missing a deadline leads to a degraded performance but not in system failure. It can tolerate slight delays. Our project falls here. A slight delay in spinning or displaying the message doesn't cause system failure, it just affects user experience. Timing is important, but occasional delays are tolerable. Washing machine and video streaming app are some of its examples. Understanding this classification helped us structure our logic accordingly, especially for things like cycle timing, button response, and safety checks like door lock status. With this strong foundation, we began designing our solution using a state machine approach. In the next part of our presentation, we'll show you how we defined each state, mapped out the logic, and verified the complete functionality through simulation using PICSIMLab. Stay with us, this is where it gets technical and exciting.
Hello everyone, my name is Gautam. Before we dive into the technical details, I want to take a moment on behalf of our entire team to extend our sincere thanks to Emertxe for providing this free online internship. This program has been an invaluable experience for all of us. It allowed us to move beyond textbook theory and gain the practical skills outlined in our internship goals. We learn how to program a microcontroller in embedded C, understand its architecture, and most importantly, master an industry standard toolchain to see a project through its entire life cycle, from requirements to a working simulation. Now, I'd like to show you exactly how we applied these learnings by walking you through the technical execution of our project, starting with the problem we were tasked to solve. Our fundamental challenge was to design and simulate a microcontroller based washing machine. The key constraints were to implement the control logic using a state machine and to do this entirely in a virtual environment. This meant using the simulated inputs from a virtual switches and providing feedback on a virtual CLCD display with no physical hardware needed. This clear problem statement this clear problem statement defined the scope and focus of our entire project. To tackle this, we first established a clear set of high-level requirements. Our primary objective was to design and implement the complete control logic for this washing machine simulator. The platform we worked on was a simulated PIC Genius development board. The brain of our operation was the PIC16F877A microcontroller, and a robust and widely used chip perfect for this kind of control application. And the entire simulation was brought to life in our virtual lab, the PICSIM lab environment. Building on those foundations, we then defined the specific inputs and outputs our microcontroller would manage. For our key inputs, we used virtual tactile switches to mimic user interaction. These included switches for power, for navigating through menus, for starting or stopping a cycle, and importantly, a switch to simulate the door status. For our key outputs, the primary feedback to the user was a 16 into 2 character LCD, which displayed all status messages. We also used a buzzer for audible alerts and controlled the onboard DC fan in PiximLab to visually simulate the motor's action during wash and spin cycles. With the requirements clear, we move to the design phase. This block diagram shows the high-level architecture of our system. As you can see, at the very center is our microcontroller. On the left are four inputs, the switches for power, pause, navigation, and door status, feed information into the microcontroller. Based on the logic we programmed, the microcontroller processes these inputs and then controls the outputs on the right. It sends text to the display, activates the buzzer when needed, and drives the motor. This design clearly maps the flow of information and control for our entire system. Now, I'd like to walk you through the step by step process we followed to bring this design to life. It was a structured, six stage approach that reflected a real world development cycle. We begin with the requirement analysis, carefully studying the document to understand every feature. Next was system design, where we created the block diagram you just saw. Then came the simulation setup in PiximLab, where we configured our virtual board. The core of the project was software development in MPLabX IDE, where we wrote the embedded C code for our state machine. After coding, we used the Xe8 compiler for compilation, turning our C code into a .hex file. And finally, we entered the simulation and testing phase, loading the hex file into PiximLab to run, test, and debug our program. This entire process was made possible by a specific set of professional tools, our development toolchain. First, we had MPLabX IDE, our main workspace for writing and managing the code. Next, the Xe8 compiler, which acted as our translator, converting our C code into machine language that the PIC microcontroller would understand. And finally, PiximLab Simulator, a virtual laboratory. This tool was crucial as it allowed us to test our application in real time by loading our code and interacting with the virtual components, all without needing physical hardware. Mastering these tools and following this structured process enabled us to successfully take our project from a concept to a fully functional simulation. Thank you. I will now hand it over to my colleague to discuss implementation details.
Hi, I'm Tanmay. Now I'll explain how we implemented the washing machine simulation using control logic. We used a state machine model, which means the washing machine operates by moving from one defined state to another based on user inputs. The first state is called idle. This is where the machine waits for the power to be turned on. When the user presses SW5, which is the power switch, the system transitions to the next state. After turning on the power, the machine enters the program selection state. In this state, the user can use SW4, the navigation switch, to scroll through different washing programs like quick wash, normal, or heavy duty. When the desired program is shown, a long press on SW4 confirms the selection. Next, we move into the water level selection state. Again, we use SW4 to choose between low, medium, or high water levels depending on how many clothes we are washing. This gives a more realistic user control experience, and the current selection is displayed on the Once the program and water level are selected, we reach the ready state. Here, the LCD prompts the user to press start. At this point, the user can either press SW5 again to start the wash or press SW6 to go back and make changes. If the user chooses to start, the machine enters the active state. This is where the washing, rinsing, and spinning operations take place. A timer runs during each cycle, simulating the duration of the wash. The onboard DC fan in the simulation visually represents these operations. There's also a safety mechanism. The system continuously checks the status of the door using SW1. If the door is open during the process, the system can pause automatically. The user also has the option to pause manually using SW6. Once all operations are completed, the system transitions into the complete state, where it displays a final message like washing complete. This marks the end of the cycle and brings the machine back to its idle condition. This slide shows actual LCD screenshots from the simulation. These helped us test and verify that the machine transitions correctly through each state. In the first image, we see the power on prompt. The machine is in idle state and it waits for the power button to be pressed. In the second image, we are in the program selection screen. Here, the user can scroll through available programs using SW4. The LCD updates in real time to show the selected program. The third image shows the active cycle screen. A countdown timer appears on the LCD to simulate the ongoing wash or spin cycle. This makes the simulation feel more real, similar to modern washing machines that show the remaining time. This slide focuses on two important features we implemented for realism and safety. First is the door open alert. The system constantly checks SW1, which simulates the door switch. If the door is open during washing, the machine pauses automatically and displays a message like door open paused. This is similar to how real machines lock the door during the operation. Second is a completion message. Once all cycles finish, the LCD shows a final message like cycle complete or washing done. This lets the user know the machine is ready to be used again. We could also activate a buzzer at this point to alert the user.
Hi all, I'm Ronak Singh and I'll walk you through the implementation part of our project. I'll explain how the code is structured across the different files and how each selection contributes to simulating the washing machine's behavior. Let's start with the main.h file. This header file includes all necessary definitions and hardware mappings used across the project. We define screen states like washing program screen, water level screen, start screen. These are used to control which stage the user is in. Next, we define hardware pin macros for buzzer and motor, RC1 and RC2. These pins control physical actions like buzzing or simulating fan spinning. Moving to washing machine header, this is a function declaration file where we list all the major routines we implemented. These functions are defined later in washing machine functions.c file. Now let's look at main.c file, the heart of our program. This is where everything starts. Init config function. We begin with init config, where we initialize CLCD display, keypad input, timer, and enable interrupts. We also set pin directions for buzzer and fan and turn them off initially. The main function begins by displaying press key 5 to power on washing machine. It says in the loop until switch 5 is pressed. After that, it calls power on screen for animation and setup. Inside the infinite loop, we read key presses and transition between screen states, from washing machine program selection to water level selection to start stop screen selection. And finally to the run program function, which performs the washing. The switch case at the end determines what function to call based on the current operational mode. Now let's move on to the washing machine functions.c file. Now let's look at washing machine functions.c. We define all our core logic. This shows a loading animation using LCD block characters and displays powering on washing machine to mimic a real appliance behavior. Washing program display. This function allows user to scroll through 12 washing programs using switch 4. The currently selected one is shown with an asterisk and the list wraps around at the end. Water level screen, similar to the program selection, is this shows auto, low, medium, high and max water levels. Selection is made using switch 4 again, with screen reset flags helping cleanly transition. And finally, the run program. This is the most important function. It handles door status using door status check, displaying selected program and time, dividing time into wash, rinse, and spin cycles, countdown using timer, detecting when time is up and transitioning to program completion. It also responds to switch 5 to resume and pause, switch 6 to resume mid operation, and door open, which stops everything, turns on buzzer, and displays warning. Door status check. This safety function ensures that if the door is open, the system turns off the motor and timer, and it activates the buzzer, displays door is open, and close the door. Only when the door is closed, everything resumes. This is how we simulate real world safety features. So now let's have a look at how all the things actually work with the LCD and the switches. So I'm on the home screen right now and it says press key 5 to power on the washing machine. So the key 5 is the RB4 button. I'll press this button and as we can see the washing machine is powering on. After the machine is on, we can see the list of different washing programs. We can uh, scroll through it and choose our desired washing program. I'll go with delicates. I'll have to long press the button to select the program. Now I'll have to select the water level. I can leave it to auto, or I can also change the water level. We have different modes like low, medium, high and max. I'll go with high. Now it says press switch 5 to start and switch 6 to stop. If I press switch 6, it will take me to the home screen again, and I'll have to repeat the whole process again. In case if I selected any wrong option, I can always go back to the home screen and start the whole process all over again. Let me demonstrate it to you. So I'll press switch 6. So I'm now again on the washing program screen. I can change my option and I'll go with whites. Now I can also change the water level again. Now finally we'll start the washing process. I'll press the switch 5 to start it. Okay, so as we can see, the washing has successfully started. The function is the machine is currently washing and the timer says it has 1 minute and 6 seconds left. We can pause this process with switch 6 and again start it with switch 5. So if I click the switch 6, the washing process should be stopped. As we can see, it is completely stopped. The timer has stopped at 51 seconds, and if I again want to start the process, I will press the switch 5. So the machine has started and the timer has also resumed. We will shortly see. Okay, so here's the change in the function. The washing process is complete and we are in the rinse stage of the whole process. It will shortly turn into spinning. Let's wait for it and see. Okay, so it says the clothes are rinsed and it started spinning to dry them up. Okay, once the process is complete, the buzzer is buzzing and we are back again on the home screen. Okay, I think I missed one feature of this washing machine, which was the door open. So let me demonstrate it again. I'll go with something which completes faster. I'll go with all the default options. I'll leave it in to auto. Let's start. Okay, so we'll have to wait another 20 seconds. By this time I'll demonstrate to you how the door function works. So if I press this key, if I hold this key, it means the door is open, and as we can hear, the buzzer is buzzing and it alerts us that close the door. And when I release the key, the washing progress resumes. So this was all about the simulation of the washing machine. Okay, so this is all about our project, and now I'd like Tanmay to conclude this presentation.
To conclude, this internship project gave us hands on experience in embedded systems without requiring physical hardware. We learned how to simulate a complete appliance from powering on to completing a washing machine using just software tools. This helped us bridge the gap between academic theory and real world practical applications. Tools like Pixim Lab made it possible to build and test the project entirely in a virtual environment, which is a huge advantage for learning and prototyping. Overall, this project strengthened our understanding of microcontroller based systems, user interface design, and safety logic, all of which are crucial for automation and IoT development. Thank you, Emertxe, for this internship opportunity.